So continuing with our problem solving, here's another case of displacement current. You might want to picture this as a parallel plate capacitor where the plates are made out of circular discs. So if you're looking directly down at the arrangement of plates, then your view shows the circle head on, and we're told that there's a current density, a displacement current density of 3.6 amps per square meter, and we need to find the magnetic field 4 centimeters from the center. So the radius is 5 centimeters, and we're asked to find the magnetic field at a radius of 4 centimeters. So we can use Ampere's law. The integral of B dot ds equals mu naught times I enclosed. In this case, the current enclosed is displacement current. I've already shown my Amperian loop. It's just a loop with a radius lowercase r. So the left side of the equation becomes very simple. This is B times 2 pi r, and that equals mu naught times the amount of current enclosed. Well, here we have to integrate. We aren't given the displacement current, we're given the displacement current density. So I have to take the integral of j dA. As r goes from 0 to 4 centimeters, I'll just say from 0 to lowercase r. But the current density is uniform, so I could take it out of the integral. So we have B times 2 pi r equals mu naught times j, and then all we're left with, the integral of dA, is just going to give us the area contained by our Amperian loop. So this is just pi r squared. We can cancel the pi, cancel one of the values of r. So we have the magnetic field is equal to mu naught j r over 2. And all that's saying is if we make a graph of magnetic field strength versus r, from the center of this circular parallel plate capacitor to the edge, the magnetic field grows linearly. I'm going to guess from there onward it drops off as 1 over r. Okay, if we want to plug in numerical values, we have B equals 4 pi times 10 to the negative 7th Tesla meters per amp, multiplied by 3.6 amps per square meter, multiplied by 0.04 meters, divide by 2. Let's see what this comes out to dimensionally before we grab our calculators. Amps cancel amps. These meters get squared and cancel with those square meters, and we're just left with Teslas. That's perfect. So we get 9 times 10 to the negative 8th Teslas. Question goes on to ask, what's the magnetic field at a point 8 centimeters from the center? So again, the integral of B dot ds is equal to mu naught times I enclosed. The amount of current that's enclosed, there's only displacement current. Out to the edge. Beyond there, right, from 5 centimeters out to 8 centimeters, there's no more displacement current. So to find the amount of current enclosed, the left side of the equation is obviously just going to be B times 2 pi r. The right side of the equation is mu naught, and we're going to take the integral of j dA once again, but instead of integrating from 0 to lowercase r, we're integrating from 0 to capital R. We're only accounting for current density up to capital R, up to 5 centimeters. like I say, beyond 5 centimeters out to 8 centimeters, there's no more displacement current. So again, the J comes out of the integral, and we've got, move up to here, B times 2 pi lowercase r is equal to mu naught J times pi capital R squared. So we can cancel out pi, and we have B equals mu naught J times capital R squared over 2 lowercase r. So it's 4 pi times 10 to the negative 7th times 3.6 times 0.05 squared divided by 2 times 0.08. And in this case, we get 7 times 10 to the negative 8th Teslas. Amateur radio operators, or ham radio operators, they're often called, are not allowed to broadcast with signals whose power is any greater than 1,500 watts. If the radio signals from their antenna spread out spherically and isotropically, meaning with the same intensity in all directions, what would the intensity be at a distance of 100 kilometers? So here's their radio antenna. Electromagnetic radiation spreads out spherically, so we can draw spheres of different radius. And if we imagine out at a distance of r equals 100 kilometers, or 1 times 10 to the 5th meters, then what's the intensity at that location, assuming that the power is the maximum power of 1,500 watts? Well, intensity is just power per unit area, so it's 1,500 watts divided by the surface area of the sphere, which is 4 pi r squared, so we have 1,500 watts divided by 4 pi times 1 times 10 to the 5th squared, 1 times 10 to the 5th meters. So our units will be watts per square meter. No special name for that. And we get about 1.2 times 10 to the negative 8th watts per square meter. What's the wavelength if they're broadcasting at a frequency of 14.3 megahertz? Speed is equal to frequency times wavelength. In this case, since it's radio waves, which are part of the electromagnetic spectrum, it's the speed of light. So we're asked to find the wavelength. The wavelength is equal to the speed divided by the frequency. So it's 3 times 10 to the 8th meters per second divided by 14.3 megahertz. So mega is 10 to the 6th. And another way of thinking of hertz is just 1 over seconds. So the seconds cancel out, and we're left with meters. And we get a wavelength of about 21 meters. How does this compare with commercial AM and FM broadcasts? So you've probably noticed on your radio, if you're tuned to the AM band, then it typically says KHZ. The FM band is always followed by some number of MHZs. So you might listen to, I think there's a news radio channel that broadcasts at 1070 kilohertz, or some sports broadcasts are on 570 kilohertz. I think those are a couple of the presets I have on my AM radio in my car. 106.7 megahertz, 95.5 megahertz. Those are some presets I have on my FM band. So how does this compare? How does 14.3 megahertz compare to commercial AM and FM broadcasts? Well, it's somewhere in between. It's a very low frequency in terms of millihertz, megahertz. So I think the lowest on the FM band is somewhere around 88 megahertz. And then the highest value on the AM band is somewhere around 1500 kilohertz, which you could call 1.5 megahertz if you want. So 14.3 megahertz is beyond the highest frequency broadcast on commercial AM radio, but it's below the lowest frequency broadcast in FM. So it's a part of the radio spectrum that's not reserved for commercial broadcasts, but for amateur broadcasts. We can skip this problem. Average solar intensity just beyond the Earth's atmosphere is just shy of 1400 watts per square meter. Due to the fraction of energy that's absorbed by the atmosphere, the intensity at the surface is about 1,000 watts per square meter, but of course that depends on where you are on Earth, the latitude, the seasons, the amount of cloud cover, and other variables. What minimum area of solar panels would be required to simultaneously power a 3 kilowatt air conditioner, a 1.5 kilowatt hair dryer, a 450 watt garbage disposal, a 2 kilowatt microwave oven, and a dozen 12 60 watt light bulbs? So let's add all this up. 3 kilowatts, or 3,000 watts, plus 1,500 watts, plus 450 for the garbage disposal, plus 2,000 for the microwave, plus 12 times 60, should be 720 watts. So we add this all up. We get a total of 7,670 watts. And so let's assume the best case scenario where you can get the full 1,000 watts per square meter at the surface of the Earth. So intensity is power over area, and we're asked to find what minimum area of solar panels. So the area is equal to power divided by intensity. So 7,670 watts divided by 1,000 watts per square meter just gives us 7.67 square meters. So if you want your solar panel in the shape of a square and not a rectangle, each side would have to be about 2.8 meters, which would be about 9 feet. If you had a 9 foot by 9 foot solar panel, you could power all those devices at once if you were exposed to maximum intensity of solar radiation. So you probably have to use this as a baseline and then work up from there for the case of what latitude you happen to live at. A spacecraft similar to the one shown below, I don't know how well you can see this. So there's the spacecraft, and there are some tethers connecting to a giant solar sail. So some big surface area that is exposed to the intensity of light, and because of the radiation pressure, there's a force exerted on that sail that can propel the spacecraft. So we're given that the area of the sails is 3,000 square meters, and The star delivers light with an intensity of 2,000 watts per square meter at the location of the spacecraft. What amount of force propels the spacecraft? So we're looking for force. We are given intensity, 2,000 watts per square meter, and we're given area, 3,000 square meters. So force, well, pressure is equal to force over area. So force is equal to pressure multiplied by area. So we can use the intensity to get the radiation pressure. Now we'll assume that it's a perfect reflector. Oh no, the problem tells us the sail is a perfect reflector. So in that case, the radiation pressure is equal to 2 times the intensity divided by speed of light. So 2 times 2,000 divided by 3 times 10 to the 8th. This gives us a pressure of 1.33 times 10 to the negative 5th newtons per square meter, or pascals if you prefer. So then force is equal to pressure times area. So it's 1.33 times 10 to the negative 5th newtons per square meter multiplied by 3,000 square meters. And this gives us a force of 0.04 newtons. Not a whole lot. To get a sense of how large that force is, the question is, how does it compare to the force of gravity between the 800 kilogram spacecraft and the nearby planet with a mass of 5 times 10 to the 23rd kilograms? We'll assume the spacecraft is at an orbital distance of 9 times 10 to the 7th meters from the center of the planet. So here we need to rely back on Newton's law of universal gravitation. Force is equal to universal gravitational constant times the mass of one object multiplied by the mass of the other divided by the distance between their centers squared. So we have a force of 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared multiplied by 800 kilograms for the mass of the spacecraft. Multiply that times 5 times 10 to the 23rd kilograms for the mass of the planet, and divide that by 9 times 10 to the 7th meters. And don't forget to square that distance. And this comes out to a force of about 3.3 newtons. Okay, so the force from the solar wind or radiation pressure, photon momentum, or whatever you call it, is pretty small in comparison to the force of gravity, so probably wouldn't have a significant effect if this spacecraft is anywhere near this planet here. But if the spacecraft were far removed from this planet in the far reaches of outer space, well, if it were in the far reaches, I guess there'd be no star to propel it. But if it was far from any planets but close enough to the star, then the net force, albeit pretty small, it would produce a small acceleration. But if applied for a long enough time without any resistance, as there's a lack of air resistance, of course, in interstellar space, then this presents a realistic mode of propulsion for spacecraft.